Hello, Math 1224. This is Dr. P with Lesson Launch 10.3, The Long Way Around. So I've written down a polar function here, r of theta equals 3 plus cosine of theta. This is going to trace out some kind of curve in the coordinate plane if I plot this using polar coordinates. The question I want to ask here is, if I sketch the curve created by this polar function, how long is the curve? How long is the curve? So in order to help us get started, I'm going to start by sketching this graph. I thought this would be a good chance to demonstrate how we think about a function like this. I feel like the rose I created, the one with the 3 petals in lesson launch 9, was actually kind of a complicated example to start with, and I slightly regret starting with it. I think this might have been a better example. So this is a chance to think about how we graph a function in polar coordinates. So again, this is going to be my x-axis and this my y-axis. And to graph, I'm just going to start thinking about what is r of theta at various values of theta. And I'm just going to sketch a few, or create a table with a few nice little reference values in it. So if theta is 0, then r of theta, that's going to be 3, plus the cosine of 0, that's going to be 4. So when theta is 0, my radius is going to be 4. In fact, let me just go ahead and put tick marks here so that we have some indicator of what's going on. There we go, 1, 2, 3, 1, 2, 3. There we go. Sorry, probably a real professional would have had those in place before we get started, but anyway, when theta is 0, so I'm looking in this direction, my radius is 4, so I'm going to put a point there at 4. When theta is pi over 2, my r of theta is going to be 3 plus the cosine of pi over 2, which is 0. So I'm going to have r of theta equals 3 at that point. So as I look in this direction, my radius is going to be 3. My distance from the origin is 3. All right, and then as I come back to theta equals pi, well, cosine of pi is negative 1, so r of pi is going to be 2. That's 3 plus negative 1. So as I come back here, I'm going to be at this point here, radius of 2. And then at theta equals 3 pi over 2, r of theta is going to be 3 again, because cosine of 3 pi over 2 is also 0. And then eventually I return to 2 pi, and cosine of 2 pi is back to 1. So my radius is back at 4 again. And in fact, that's not going to create a new point. That's the same point I had earlier. And this function is actually going to be periodic. It's periodic with period 2 pi, which means that as I make a full rotation around this figure, come back here, what happens after that is just going to be a repeat of this. It's not going to be like the spiral where it keeps spiraling out forever. This is going to be a nice little closed curve. And that curve is going to look something like this. So my radius here is 4. My radius is gradually going to decrease to 3. And then it's going to continue to decrease and eventually become 2. Let me just draw that again. Eventually going to become 2. That's where it's the shortest. And then get longer again. And then increase out to 3 again. And then eventually increase to 4. And it's probably going to be smooth the entire way around. I don't think there's going to be a cusp or anything. But this figure, I don't know how much education you all have in polar coordinate graphs. I hope not very much, because it's probably time you could have spent doing something different. But this one, we had to learn about all of these in pre-calc when I was in high school. And this one, I believe, is called a limaçon. And it's the fancy French C with the beard. I don't know what that stands for. It has been suggested to me by Xander during our meeting prior to their presentation, him and Walter, that this might be French for lima bean, because L-I-M-A, and it does look kind of like a bean shape. It looks more like that if you change the ratio of these coefficients a little bit. But anyway, that's the curve, and now I want to see if we can figure out how long around this curve is. Now to do this, we need to think a little bit about what it means for a point to be a point on this graph. So let's say I have some point here. So if I have a point here, then that means that theta, my direction, is going to have some value in radians, and this distance is going to be r of theta. And now I can actually write down exactly what this point is going to be, because I know that if my radius, or my distance from the origin, is r, then the coordinates of this point are going to be r cosine of theta and r sine of theta. And remarkably, that has absolutely nothing to do with this function here. This function is what's creating this graph. But for any point on this graph, the coordinates of that point are always going to be the radius or distance from the origin times the cosine of this direction, and the radius times the sine of that direction. And that's just unit circle or circle of radius r trigonometry there. Okay, anyway, so what does that mean? Well, r, you'll remember, is determined by this function here. So that means that the coordinates of this point are going to be, oh boy, am I going to have room to write this? Let's see. Well, r is 3 plus cosine of theta. So this is going to be 3 cosine theta plus cosine squared theta. You know what? I'm just going to move on to the next line. The y-coordinate's going to be r, that's 3 plus cosine of theta times sine theta. That's going to be 3 sine theta plus sine theta cosine theta. And those are going to be the coordinates of that point. Now, for my next trick, I'm just going to zoom out on that. For my next trick, I'm going to think about how that position varies if I change theta by a little bit. So I'm going to create a blown up version of this graph. I'm just going to try and get the basic shape right here. I'm not going to try and put quite as much effort into getting the coordinates exactly perfect, because this is really more of a tool to help us think about the geometry. By the way, I'm just sitting here in awe of how good of a job I did of getting that shape, pretty much the same as the first one I drew, just by doing a quick sketch. Maybe I should have done that the first time. Anyway, so let's suppose I'm at some point here. So that point corresponds to an angle of theta. Now, suppose I change theta by a little bit. So I create here a new new ray by changing theta by some tiny angle d theta. And I realize in that picture d theta does not seem all that tiny, but I have to do this or the picture is not going to be visible to you. So anyway, the question I want to ask is, how far do I go? How far do I go as I change theta by d theta? That's the question. All right. So now to think about this, the way I'm going to think about this is, first of all, I'm going to rewrite my function here. So I have that at hand. R of theta equals, let's see, that was 3 plus cosine theta. All right. Now I started here at the point, you'll recall this was, what was it? Let me just look. There it was. It was 3 cosine theta plus cosine squared theta, comma. Okay, I'm going to move that back now. And the other coordinate was 3 sine theta plus cosine theta sine theta. Now, what we're going to do is we're going to consider how each of these coordinates changes, this one and this one. How do these change as theta changes? In other words, what's their rate of change? Their rate of change with respect to theta. Well, thankfully, we have a tool for finding the rate of change of something. That's the derivative. That's what you spent all of last semester on. So I'm going to calculate the derivative of each of these with respect to theta. So those derivatives are going to be, so actually, just for the sake of having some notation, let me call this x of theta and this y of theta. So those will tell me the x and y coordinates that we're at any given value of theta. All right, so the derivative of the x coordinate, x prime of theta, that's going to be, let's see, the derivative of 3 cosine theta is negative 3 sine theta. And then the derivative of cosine squared theta, I believe, is going to be minus 2 cosine theta sine theta. Can't forget about that sine theta. That's the chain rule there. And then the derivative of y prime of theta is going to be 3 cosine of theta plus, and then let's see, this one's a little bit trickier. I'm going to need to use the product rule here. But I think I'm going to get cosine squared theta, that's one term, and then minus sine squared theta. All right. So now if I look at this picture here, see if I can get all of this into one frame here. So as I move from this starting point here to my next point, I'm going to move some small distance, and my x and y coordinates are both going to change. The rate at which they change is given by this formula and this formula. So if I change d theta by a small amount, then my predicted change in x, let me write this in a different color, predicted change in x is going to be delta x equals that first derivative there, minus 3 sine theta, minus 2 cosine theta sine theta, all of that times delta theta. That's the linearization formula that you learned in Calc 1. And then the predicted change in y, that's going to be delta y equals 3 cosine theta plus cosine squared theta minus sine squared theta delta theta. All right, so what does that mean about the distance that I've moved? Well, the distance I've moved, that's going to be, whoa, pull that out there. Okay. That distance I've moved, actually, you know what? I want to zoom in quite a bit because I want to show you something. Because the distance I've moved can be thought of as the hypotenuse of a right triangle. This is the distance I'm moving in going from one point to the other. Well, that distance is made of some change in vertical position, delta y, and some change in horizontal position called delta x. So that distance is going to be the square root of delta x squared plus delta y squared. So taking that principle and applying it to this problem, see if I can get all that in one frame there. I'm constantly amazed at how much I can get into one frame if I zoom out enough. Anyway, so my distance over a small change in theta for a small change in theta is going to be the square root of some real nastiness here. Now, I'm not going to lie, this is going to be really gross. Negative 3 sine theta minus 2 cosine theta sine theta. All of that times delta theta quantity squared plus, oh boy, going to need a bigger boat here, plus, see if I can get all this in here, 3 cosine theta plus cosine squared theta minus sine squared theta times delta theta, all of that squared. Now, one thing you'll notice is that each of these terms here is going to have a delta theta squared because that's getting squared. Same here. That delta theta, I can actually pull it out, and I get the same thing negative 3 sine theta, etc., etc. I'll just write. Saying it makes it feel even more tedious than it is sometimes. Here we go. All of that, and then you'll notice I am very markedly closing that square root symbol. All of that times delta theta. So if we want to know the entire distance around this figure, it actually is possible for us to write an integral that represents that, because this nasty expression here tells us how far we've gone over a short increment of after a short increment of direction. Sorry, after a short increment of theta. So the total distance is going to be the integral from 0 to 2 pi, because that takes me all the way around the figure, of the square root of pretty much everything I just said. Now, I'm actually going to do a little bit of tidying up this time because those negative signs in that first square, they're not necessary. I could just take the opposite of the whole thing. The square is going to wind up being the very same. I'm not going to make any adjustments to the second one, just going to leave it as is. all of that squared. And then at the end, I've got a big old d theta there. Okay, now let me tell you a secret. I am probably never going to ask you to evaluate one of these by hand. It turns out that the set of examples of arc length calculations that you can seriously evaluate by hand, there's about 3 of them in the entire universe. I'm not even kidding. The examples of arc length that you can compute analytically, it's such a small set that really we just sort of give up. I'm not just saying that we're giving up for the hell of it. We're giving up because the calculations are usually impossibly hard. Instead, we calculate these numerically. And that's exactly what I'm going to do here. So we're going to calculate numerically using my favorite device, Wolfram Alpha. Wolfram Alpha. You could use something else if you wanted to. You could use your graphing calculator. I'm going to use Wolfram Alpha. Now, last time I tried pulling a web browser into my video, it did not go so well. So rather than repeat that nightmare, I'm just going to pull up Wolfram Alpha on my laptop. You can do the same thing if you feel like it. I'll run the calculation there and I will report back what I get. So I'm going to pause my recording for just a second while I do that. Okay, so I've run the calculation and Wolfram Alpha said something very funny. You should try it yourself just to see what happens. It found this perfectly reasonable, and it gave me an answer of something called 16e of 3/4. Now that's a capital E, that's not a little e. And in the annotation, Wolfram Alpha says E of m is the complete elliptic integral of the second kind with parameter m equals k squared. I have to be honest, I have no idea what that means. I think it'd be very interesting to find out. But it also gave me a numerical value, which is what I was really after in the first place. That numerical value was approximately 19.3769. That's the numerical value it gave me. Now, I always like to run a little reality check on what we're doing, just to see if that tracks reality in any way. I like to see if that's a reasonable answer to the question I originally asked. So let's go back to my original picture here. Again, that value was 19.3769. So should we find that value plausible? Well, when you look at this figure here, this limaçon, this is certainly not a circle. In fact, pretty much by definition, it's not a circle. The radius varies depending on theta. But that being said, it does kind of approximately track a circle of radius 3. Sometimes it is further out, sometimes it's closer in, but it feels kind of like a circle of radius 3. And the circumference of a circle of radius 3 would be circumference of circle of radius 3 would be 2 pi times that radius. That's 2 pi times 3, which would be 6 pi, which comes out to approximately, I don't know, I think that's about, I'm mentally calculating now, which is silly because I have Wolfram Alpha up right over here, but I think it gives me about 18.84, give or take. And that's actually not so bad. That's very reassuring to me, because here, I don't expect this to have exactly the same circumference as a circle. It is longer in places, it's shorter in places, and the longer parts probably don't exactly compensate the shorter parts. And in fact, I probably should expect it to be a little bit longer because of this part out here that bows out further than a circle of radius 3 would. But those numbers are awfully close to each other. So I think that, and that's no guarantor, of course, that I did the calculation correctly, but it does suggest that we've come up with a viable method for finding the arc length around a polar curve. Now again, just for emphasis, the integral that we came up with was this nastiness here. It's hard to fit in one frame. So if I ever ask you about one of these, the goal is going to be to write it down and then calculate it numerically. It's not going to be ever, as far as I can think of, to evaluate it analytically. It's just nice knowing that there is a way in the world to solve this kind of problem and even come up with a reasonable numerical estimate. So anyway, I hope that the geometry in that video made sense. That's the main thing. Please do ask questions if you have questions. There's a lot going on there, so I look forward to hearing what you think. See you in class.